Hello, everybody. This is another Zoom interview back by popular demand. Geologist Dave Tucker from Bellingham, Washington, longtime geologist, person associated with Western Washington University. Dave, dare I ask, what's the weather like up in Bellingham this afternoon?
I'm looking out my window. I see a few patchy clouds. Otherwise, it's sunny and warmer than it's been.
Holy cow. Okay. Wow. I didn't expect that answer. It's
It
been so
might
much.
even be in the mid 40s.
Holy cow. Okay. Well, all things are rosy over there on the western side of the crest. I love it.
Well, it's pretty nice. Come on over.
Yeah, I would love to. I would love to. Thank you. Um, this is part two, viewers. If you missed the first visit with Dave Tucker, that was last October, I suppose, and we were talking about the basics of the Hannegan caldera, other potential calderas, and other known caldera in the Mount Baker area up there in the northwestern corner of Washington. And Dave is back to give us a little bit more detail on maybe how you map a caldera in the field and other details, because we are thinking about calderas in the series as we wrap up the alphabet. Dave, I know you have a few slides. Do you have any opening comments about what you're hoping to do with this here this afternoon?
Sure. I thought the idea, Nick, would be to show a sequence of cartoons that I made showing the process of a Cascade style caldera collapse. So we're not talking giant calderas like Yellowstone here. Remember, we're talking about much smaller structures, something like the Crater Lake caldera being a very large example of a Cascade caldera. Most are smaller than that. Um,
Let's do one more verbal thing because that intrigues me right off the bat. So, in addition to being a smaller scale compared to Yellowstone caldera, are there a couple of other uh, notable features that identify it as kind of a classic Cascade style caldera?
no, not necessarily.
Yeah.
Other than they tend to be small, and of course they're in the
Okay.
mountains. One
Yeah.
reason they
Okay.
tend to be small is they're in a compressional tectonic setting, and so these things tend to be localized and more compressed, if you will.
Okay. I got one more. I'm excited. I can't stop. In either case of the known calderas that you've worked on, whether it was Hannegan or Colshan, were there prior volcanic events at that spot before that caldera? Either of those calderas showed up, or are they blasting and sinking in kind of virgin ground that's not even got a long history of volcanism there? Do you any
In
evidence of that?
in the case of the Hannegan caldera, the older one, which is 3.7 million years old,
Yeah.
still young, much younger than most of the ones that we'll talk about otherwise.
Okay.
Uh, there, there's no volcanic structure outside of the caldera, but
Hmm.
inside the caldera are blocks of older volcanic rock. So we know that the Hannegan caldera erupted up through some sort of an existing volcanic edifice,
Hmm.
andesitic volcanic
Hmm.
edifice, and
Hmm.
the only evidence for that prior volcanism are blocks of volcanic rock inside the caldera fill. In
Inside.
the case of Culshan caldera, which is only 1 million years old and on the very northeast flank of the Baker volcanic field, there are no volcanic rocks preserved that are within the caldera structure. There are some older dikes that are exposed, but no real structure. So we think there must have been volcanism, preceding volcanism in both areas, but in the case of Culshan, probably very limited.
Huh.
In the case of Hannegan, perhaps larger.
Does that mean there are exotic blocks, like hundreds of millions of years old, of exotic terrain material that is in the blocks within that Colchian caldera?
No, not in the Culshan caldera. Yes, sure, there are non-volcanic blocks from the surrounding terrain,
Yeah.
Nooksack Group and
Right. Okay.
and green schist and that stuff from Mount Chuckson. In the
Yeah.
case of Hannegan, there are volcanic rocks which are certainly older than 3.7 million years old, but they
Yeah.
weren't any good for dating.
Got it. Perfect. Thank you. Thank you for playing
Sure.
along. Let's go to your slides, Dave. And I'm just happy to sit back and relax and enjoy what you have for us. I might interrupt a little bit, but I don't want to that much. I think you're going to get on a roll here with some of your figures, and we're very much looking forward to it. So please,
All
let's
right.
do
The
it.
first one I'm
Yeah.
going to show
Hmm.
is the first one I'm going to show is the location of where we think some of these calderas are in the Cascades.
Okay.
So I did a paper with the lamented and recently died Paul Hammond, who you featured on Hammond Land
Yeah.
recently.
Yes.
And he and I put together a publication for the GSA national meeting in Portland in 2009, in which we attempted to uh, locate calderas and possible calderas in the northern part of the Cascades, which we defined as in Washington state.
Hmm.
So each of these little circular areas here is what we believe to be a caldera and its age, approximate age,
Hmm.
um, or possible calderas because the field evidence is scanty.
Hmm. Yeah.
So, for instance, here the Quartz Creek caldera is published by Russ Everts in 1987, 23 and a half million years old.
Hmm.
Some of these, for instance, like MD is Mount Daniel, and it was touched upon in a thesis, geology master's thesis by a fellow named Simonson in 1981.
Okay.
And the evidence is much sketchier for whether that's a caldera or not, just a very thick exposure of what looks like caldera filling rock at greater than
Hmm.
25 million years of age.
Okay.
So some are more well defined and others are not very well defined. Um, the very few of these have actually been published on and described in the literature as calderas.
Huh.
The earliest one being the Coquihalla, um, which was published in 1980 in a Canadian paper, 21 million years old, just north of the border there. And really good evidence that it's a caldera, but they didn't call it a caldera because they didn't really know what calderas were when they published it. They were just describing the volcanic rocks.
Sure.
So that's kind of the breakdown. As you can see, there's a lot of them, and most of them are pretty old.
Yeah, they are, aren't they?
The younger ones, for instance, are Hannegan, 3.72 million years old. Very nearby Colson caldera, 1 million. The Gamma Ridge caldera, which is sketchily described, but pretty, there's no doubt that it's a caldera, 2 million years old. The Devil's Horns down here in the Goat Rocks area, approximately 3.5 million years old. It's not really very well defined, but there's very little doubt that there was a caldera there.
Hmm.
So, but most of these are not very well described, if at all.
Well, it's a great map. The data is right there as far as we know, and I thank you for including the dates of when these things were published. Makes me wonder how many more there are in the not in that map that folks just haven't looked for yet. Like, this can't
Well,
be
I
a
have to say,
complete. Yeah,
well, no, I have to say that most of this work, other than down here in what we call Hammond Land,
yeah.
most of this, especially in the northern part, is work that I did through literature searches.
Okay.
So I have
Yeah,
not been on the ground in some of these places,
sure.
but I've read the literature and I did a very extensive scouring of Cascades volcanic studies dating way, way back in some cases, 1981, 1947,
Right.
just looking for descriptions of volcanic bodies, for lack of a better term, that seem to have characteristics of a caldera deposit.
I mean, if I'm a young professor that just showed up in the Pacific Northwest and I saw this, I think I could see about 15 master's theses staring me right in the face here. I mean, there's,
Absolutely right.
yeah, right. Okay.
Absolutely right. And I've been trying to get some people to do these works, but so far not much success.
Okay. Well, we'll see what we can do about that.
Good.
Um, that's a great start. Thank you. Let's
Hey,
keep going.
okay. So now I have another illustration of how this caldera forming process begins. And so I'm not real handy with this. I'm sorry.
Take your
So
time.
we
You're fine.
so we begin with the surface, no matter what it is, volcanic, non-volcanic, mountainous or not. In the Cascades, it's probably mountainous, and a
Mhm.
large body of magma. We don't know what a magma chamber looks like,
Right.
but I just had this cartoon illustration of a large volume of magma accumulating below the surface, and perhaps some of it leaking to the surface and erupting. But due to the influx of magma and probably some lifting of the landscape, faulting beginning to occur, and those faults may become pathways for magma to reach the surface and erupt as localized volcanoes,
Hmm.
or they could even be larger ones. But as as this magma continues to accumulate, uh, essentially it breaks the surface. The
Hmm.
crust begins to subside as large volumes of magma are erupted, usually as ash, right? This is usually very gassy, silicic magma that's accumulating. And so as the magma erupts as ash, the surface collapses into the void space left, which
Hmm.
pressurizes the magma body, which continues to drive the eruption. Large pyroclastic flows go out over the countryside, just devastating everything. Some of these can spread for tens of miles around. So we're talking a uninhabitable zone remaining after one of these caldera collapses.
Yes.
And finally, when the collapse is finished, we may end up with a large tectonic depression that's completely filled with volcanic ash, with breccia lenses from the wall rock that's collapsed into this caldera structure, maybe dikes left over. Um, and there may be dikes along the margin that then erupt marginal volcanic bodies, domes, or small volcanoes. And then the outflow sheet is the ignimbrite, is the outflow tuff, um, which sits on the surface and is highly erodible.
Hmm.
So over time, these, uh, there's some very distinctive features of a caldera. Number one, ideally, you would find a dike, or at least a faulted expression on the surface, where
Mm.
one type of rock suddenly disappeared and became uh, was in contact with volcanic filling rocks, ash, tuff.
Hmm. Hmm.
There may be an outflow sheet remaining, but in the Cascades, probably not because they're highly erodible. If you get enough of a cross section through erosion, then you'll find these landslide bodies going out into the caldera.
Mm.
You may have dikes filling them. In the case of Hannegan, I didn't show it here, but in the case of Hannegan, there was a caldera lake. And so there may be lake deposits spread in here too. So you might have some sedimentary rocks that are younger than the volcanics.
What evidence do you have there was a lake in that Hannegan feature?
In Hannegan, let's see. Let's see. I don't have a photo of it, but there are some lake sediments that sit on top of the caldera filling tuff, and they have fossils in them, leaf fossils.
Really?
Yeah,
Wow.
yeah. I mean,
Okay.
that would the Hannigan story would be a completely another presentation we would have to do
Yeah.
to really
Yeah.
do it justice. It's very unique and maybe the best exposed caldera in North America.
Nice.
So then, so here we have this subsided caldera floor.
I think we're
The
still
Brett,
on the first. I think we're still on the first cartoon here, Dave.
the very first one.
I think so. Yeah. I'm sorry.
Oh my
I
gosh!
yeah.
Let me go back here.
I was waiting for the next slide. I'm not sure what's going on, but I think we're just on that first gas
Sorry.
rich mag. You're fine.
Okay.
Uh,
So this one, did we see?
yeah, I can. There we go. Now I can see the next panel. I can
All
see
right.
yellow now.
Oh,
Yeah.
very sorry.
No problem.
Okay, so here's the caldera fill that is now filling the collapsed structure where all the floor, it's called the floor of the caldera, but it was at one time the surface across here, and it's collapsed in.
Beautiful.
And in the wall rock breccia sliding into it, the caldera filling material. So once again, the characteristics ideally you would find to identify a caldera would be a fault separating one kind of rock with a bunch of volcanic fill, tuff,
Yeah. Yes.
ignimbrite. Um, if deeply enough eroded breccia lenses from the wall rock sliding in there, you could have some post caldera volcanism. Okay, now I think we're on track here.
Yeah.
Let's do this one. Share this one. No, not that one. This one. Okay.
There we go. Yes.
So here we have the aftermath. A little later cartoon I drew when I knew how to do them better without a pencil and paper.
I relate.
So here's the intercaldera fill. Here's the ring fault that surrounds the collapsed structure.
Hmm.
After the eruption, there may be post caldera eruption, volcanoes, lava flows that could possibly completely bury the intercaldera fill. So
Mm-hmm.
the outflow sheet may or may not survive erosion for very long. But in cross section, be walking along, and then all of a sudden you start, maybe you've got some outflow sheet, pyroclastic flows, and then you start walking across because you're on the surface, right? Start walking across lava flows, and then maybe you find a dike or a vent structure, and then then we got this other rock which is completely different, and then we've got this other andesitic volcanism perhaps, and then we walk off and we realize we've seen something interesting, but we don't know what it is.
Uh-huh.
If we're lucky, if we're lucky, uh, erosion may
Oh, good.
have.
Yeah.
You got this one now?
I do. Yep. Yep.
All right, good. I think I'm beginning to get the handle on this.
We're cooking now.
So afterwards, you may have an awful lot of erosion, which really changes things around and allows you to get these deep cross sections into the caldera, which is how you can really do your mapping.
Mm-hmm.
So you may end up with a circular or an oblong shape defined by this fault that separates the wall rock, we call it the older rock, and the caldera fill, and then the wall rock breccia and the caldera filling tuff. So erosion is our friend if we want to really understand the structure of a caldera. Otherwise, you're just seeing the younger stuff on top. So that's an example of what you might want to find.
Mm-hmm.
Now, here's the next one. This is a section through the Big Bosom Butte caldera, which is north of Hannegan, east of Winchester Mountain, just south of the border.
Okay.
Um, northeast of Mount Baker, about 15 miles. So
Mhm.
this was mapped out by Tabor in 2003, and into his reconnaissance scale mapping, 1 to 100,000 mapping.
Mhm.
And but there's enough remnant structure and stratigraphy here with faults to strongly suggest that this structure is a caldera.
Hmm.
It's We're not certain of the age, but it's possibly 20 million years old.
Hmm.
But so this is an example of really what these things might look like in the field. I can actually dig up a photo somewhere of of what this looks like. I didn't share that. Okay, so now I want to bring up this photo.
Oh yeah.
So this is the south face of Hannegan Peak, viewed from Hannegan Pass. And for scale, the vertical scale here is about 1,300 vertical feet.
Wow.
So when I walked up here in 1994 with Wes Hildreth, when I was helping him out with his Culshan Caldera study, we went for a hike up to Hannegan Pass because Tabor had said there were volcanic rocks up there. So we
Yeah.
went to look at this, and we right away saw, okay, this is all essentially welded tuff. It's very densely compacted tuff, less welded at the top. So this was not as compressed and not as hot when it erupted. But there's lenses. These are landslide deposits within the caldera that slid off the margin of the caldera over here somewhere and
Hmm.
slid into the caldera as it was collapsing.
Hmm.
And then this really cool looking W-shaped dike. And it's not really W-shaped because it's actually straight across, but there's gullies and ridges, subtle ribs and ridges in the caldera fill, which gives you this weird impression that you're seeing a W-shaped dike, but it's really just a cross section through a prismatic section.
Hmm.
So in the field, you might have something like this to give you a suspicion that you're looking at a caldera deposit. Very, very thick ash flow deposits and breccia.
Hmm.
On the south side of Hannegan Caldera, south of Icy Peak, which is up here to the upper right, there's a fault cutting right through that.
Yeah.
This is about 900 vertical feet.
Hmm.
One kind of rock, non-volcanic on this side, and this side, everything on this side is volcanic rock. It's tough. It's caldera fill. And it looks the same here, but that's due to weathering and dark erosion, dark staining of the rock. These are very different rocks on either side of this fault. So this is the ring fault that surrounds the caldera.
Holy cow. Wow.
This is an aerial view.
I mean,
This,
I think I'm going to interrupt you. Just keep this
yeah,
slide up, Dave. But I'm
yeah.
just I want to play off a couple of things. I think am I hearing between the lines that maybe over the last generation or so there's been debate? Like some of these, I just imagine these old school mappers are like, yeah, we got a bunch of pyroclastics and there's some faults, but there's no way that's a caldera. I don't know why you guys keep talking about caldera, Paul Hammond and Wes Hildreth and Dave Tucker and a few others. Like, I don't know, is it that kind of thing? Like this is a new way to interpret older mapping
No,
or are
no, no. It's not necessarily a new way of interpreting the mapping. It's understanding what what to look for.
mm-hmm,
So yeah,
mm-hmm,
in a way, it's a new way of interpreting some older mapping.
yeah,
Mapping isn't really that old. For
right.
instance, the mapping that shows this rock right here was originally published in my thesis
Yeah,
in 2004. So we're not
yeah.
talking ancient mapping here.
Wow. So
And
that feature wasn't even really known at any kind of scale. And you're the first
no,
to say, look, oh wow, okay, that's great.
yeah, I mean,
Wow.
it helps to have a buddy with an airplane. You can fly around and get views of these things in these rugged mountains. This,
Well,
by the
that's
way, running across the front, this is a intervening ridge between me and this exposure. So
geez.
this stuff in the foreground is not related to what we're seeing there.
Ah, wow. Okay. God,
But
that
yeah, it's in part you got to know what to look for. So, for
yeah, you
instance,
got
when Wes Hildreth hiked into the northeast flank of Baker near the Baker ski area and into a very widely, very heavily backpacked area. Um, I mean, he was in there 30 minutes. He said, "Oh, there's a caldera here." And
wow.
there had been generations of geologists hiked through here,
Yeah.
students from Western and Western faculty members, and one Western faculty member in particular thought that Mount Baker was his mountain and really resented that anybody else was poking around in there. But this fellow, now long gone, had no concept of what a caldera was, and so he didn't. He really objected to the interpretation.
Well, I had my suspicion. I didn't know, but I don't miss those old days. I got to tell you, I don't miss those old days.
Me
Seriously.
neither.
I mean,
Me
yeah.
neither.
Okay, good.
Okay, so you happy with this one? I got a couple
I
more.
I love that one. Let's keep going. You're not going to top that one, I don't think, but go ahead, please. Oh,
How's
maybe
that?
so. Maybe so.
So this is clearly a totally different scale.
Yeah.
So these little black lenses in here are fiamme. These are crushed pummices.
Hmm.
So when the magma erupts, it's silicic. In the case of Hannegan, it's a rhyolite or a dacite, rhyodacite, about 69% silica. So it erupts
Hmm.
as pumice.
Hmm.
And when these huge volumes of pumice accumulate, filling up the caldera, the mass of the deposit crushes the pumices. Think of them; they're hot and they're full of gas bubbles, right? So they collapse down and they make these little lenses called fiamme, Italian for little flames.
Hmm.
So when you see these shapes, you're seeing crushed, collapsed pumices, and this is what we call a welded tuff. So hot that the ash deposit welded itself together. But in it are also lithic fragments. These are fragments that are not related to the caldera, but are the rock that the caldera blew up through. And so included these rocks, this one, and that one, and that one are remnants of previous volcanism. So
Mm.
that's how we knew there was some sort of volcanic activity here in Hannegan before the caldera formed 3.7 million years ago.
And in
So
Colshan, there'd be similar little blocks, but they'd be Nooksack and other just
correct,
crazy exotic stuff. Wow. Okay,
correct,
that's so
correct. Well,
cool.
like I said, there's a very few older dikes around the Colson caldera, but
Yeah.
I'm pretty sure Wes determined that to the best of his field knowledge, which is quite extensive, we never
Yeah.
found any volcanic clasts
Hmm.
in the caldera fill.
Very neat.
So this rock is what that whole huge south face of Hannegan Peak looks like. This is what it
Jeez.
is.
Unbelievable.
Pretty amazing.
And it's mostly solid. It's mostly welded. There's
Oh,
not
it's
this.
rock. It's you sample it with a hammer.
Jesus. Okay.
Well, now this is also caldera fill at
Yeah,
Hannegan. You like my scale?
I do.
I obviously took this on the first day of my field work that particular day because there's no bruises on the apple yet from backpacking it around. But so this is caldera fill. This is all ash, intracaldera ash, but there's a lot of blocks in it,
Hmm.
and most of these are volcanic as well. So in this case, there's so much breccia within the volcanic deposit that the deposit couldn't weld. It couldn't compact enough because the whole thing is supported by all these blocks. So
Hmm.
there's no fiame in this deposit.
Yeah, okay.
There's pummices. They're very badly weathered and leached, and I couldn't get any decent chemistry out of them. This is also part of the Hannegan caldera fill.
How wrong is it to say that volcanic breccia is like a talus field inside of the
Yeah,
caldera
no,
wall?
that's not wrong. In part, it is a talus field. Let's
Hmm.
go back to this one, and so here we got this big black lens
Yeah.
of wall rock, and that's clearly a landslide deposit.
Hmm.
So this is all the same stuff that just
Hmm.
slid into the caldera as it was collapsing. And at the same time, it's filling up with this stuff. Then the wall collapsed, and then the eruption continued and buried this landslide. So we're looking at a 30-second interval between here and here that happened to be covered up with a landslide.
Amazing.
But other stuff is smaller fragments that were just blasted out during the collapse and the big, huge eruption cloud and then settled back down into the caldera.
Well, now I'm getting greedy. Like if we can go back, if we can go back one more time to your big
Sure.
face with the W, I mean, there's no way to talk about how much time total, is there? Like with that whole, I mean, I know it's a double trap door and all that stuff, but like, is this over the course of 500,000 years or like one Tuesday afternoon or like,
We're looking at much closer to the idea of a Tuesday afternoon, and the Mariners are getting beat. So perhaps over the course of a doubleheader.
I love it.
These caldera collapses are very rapid. I mean, they may continue for a period of days
Right.
or even weeks, but I don't think weeks. I think we're
It,
looking in the scale of days at the most for this, if not hours.
incredible, really incredible. And yeah, I mean, okay.
I'd
Yeah.
love to see one, and so would you, but we wouldn't be around to tell the tale.
No, that's right. That's right.
Okay.
Great job. You've got a few more, I can tell.
Well, I don't know if you can see this.
Oh yeah, I can.
Okay, this is
Oh,
the post.
the fine
This is
print, I can't. We'll try
yeah.
to figure out how to get that fine print visible for
I can do
our
some of that.
viewers.
I can
Okay.
do that. This is
Okay.
the poster that Paul and I put together for the GSA presentation, and it's big. It's 8 feet across. It hangs on my bedroom wall right now.
Wow.
But this is the poster that has all the table of calderas, and I'm going to get into that in a minute. But
Good.
it's got the cross section and the abstract and all that, and it's published. I can provide you with the link so that people can find the abstract, which describes this.
Thank
Um,
you.
but now let me go find one of these. There we go. Give me a second here to get this thing to open.
Mhm.
Can you see this?
We're moving in the right direction. Yes, I think I can make it out.
Okay. Well, it's still really hard to see, but what it is it's half of the table, and
Okay.
it lists, and I can provide this to you, but it lists the names of the caldera, the age, the structural diameter, 3 by 7 kilometers,
Yeah.
18 by 10 kilometers. That's Mount X that I think you may have talked about with Paul.
Hmm.
Um, and you can tell the date because we still use tertiary when we publish this.
Yeah.
And then the structures that we observed and how much is preserved. For instance, preserved volume in cubic kilometers at Crater Lake is 39 cubic kilometers
Mm.
is the volume of erupted material. Culshan is about the same. Let's see one of these. So on these probable calderas, it's kind of hard to tell because
Yeah.
there's not
Yeah.
insufficient geology. And once again, remember this is based mostly on a literature review.
Yeah.
We just don't have enough information to tell us everything we need to know
Hmm.
to say, yeah, there's a caldera there at Gamma Ridge, although it's probable.
Hmm. Hmm.
Some of the ones that we talked about that I showed in that very first map um, are even sketchier. So
Sure.
we have enough evidence to put them on the map, but not enough evidence to say for sure, yeah, there's a caldera at Kai's Peak, or there's a caldera at Clear West Peak, which is based on a little bit of field mapping and a 1986 thesis. It suggests that there's like 2,000 feet of preserved intra-caldera ash flow tuff, but we don't have enough other structures remaining, or at least that are described, for us to put a check mark and say caldera.
Well, let me ask a question right there with this map. So if I was a young professor and I said, you know what, I think I want to take a master's student, I want to go to the Clear West Peak rhyolite, and I can find that 1986 thesis, and
Sure.
I can find the Tabor 1 to 100,000 map, but how much, what would be the ideal thesis with that spot? Would it be more of a mapping project, or would it be a geochem kind of a thing, or all
These
the
are
above? Like,
these are mapping projects.
okay.
So you're looking for structures in the field and you're looking for deposits in the field, and you
Mm-hmm.
put two and two together and hopefully you get something close to four.
Mm.
So ideally, you would go into the Clear West area and you would want to find uh, a fault in more than one place that
Mm-hmm.
separated non-volcanic rocks from younger caldera filling pyroclastic rocks.
Mm.
You would want to find eroded exposure, and in something 22 million years old, you probably could, that would show these wall rock landslide breccia lenses
Yeah.
buried
Yeah.
in the intercaldera fill. Um,
Well, that'd be
maybe,
tricky. That'd be tricky business, though, Dave. We're not going to get a big wall like you had up there at Hannegan. Like,
well,
you know,
maybe you do. Maybe it just hasn't been.
huh?
Maybe when the geologists went in there, they didn't really know what to look for, and they didn't. Once again, I don't remember um,
I'm just picking it
what
randomly.
what what
Yeah.
McCullough's thesis said
Right. Right.
precisely, other than to describe a great thickness of tuff,
Huh.
silicic
Huh.
tuff. So all of these that
Yeah.
have tuff are they're silicic.
Yeah. Yeah.
They're not your andesite volcanoes.
Okay. I feel a side. I say fail tangent coming on, but I don't want to derail you here. If you've got a few more, I'll bite my tongue until the end of your
No,
slides.
go ahead.
Okay, where's all the air ash fall from this stuff? Downwind, why don't we just have blankets and blankets of stuff that still remain out in the Palouse or God knows where?
Look at the age.
I
So let's say
guess.
all this stuff is way out in the east.
Yeah,
It is older than the Columbia River basalt.
yeah, yeah, right.
It's just not preserved. There may be places, say along here on the eastern flank of the Cascades, where there
Hmm.
are some uh, preserved ashfall deposits that are, in these cases, they would have to be lithified by now. But
Yeah, I mean,
you need to recognize them for that, and they
well,
may just
yeah,
be on one little cliff face where they're left. So it's
right.
kind of hit or miss finding these things.
Like, what is the
Serendipity.
oldest? What is the oldest known ash fall deposit? Like, I've never even had that thought. Like, it's all Pleistocene, I guess. Like, is there any 5 million-year-old ash fall deposit that's like lithified, whatever? Like,
In this part of the world.
I guess, or
Yeah,
anywhere.
okay. Well, the Ellensburg Formation out here is
Yeah.
Columbia River basalt sort of ages, and there is certainly
Huh.
silicic ash within that.
Yeah.
But is it a coherent deposit that hasn't been remobilized by streams?
Right.
And
Right.
can you say that it's from here as opposed to from here?
Mm-hmm.
And it's from here as opposed to from here.
Hmm. Oh,
So when you
fun.
start getting into these really, really old deposits,
Right.
uh, you need, that's where the geochemistry comes in to say, well, this thick pile of tuff here, the Eagle tuff of Tabor matches chemically the pumice that we find over here in the Ellensburg Formation, for instance.
Okay, well, that just gives me
It's hard.
well, it's hard, but I think I have an answer. I promise I didn't have the answer before. I did some work. We're almost done with my tangent, Dave. Thank you.
I
Uh,
love tangents.
this young crackerjack geologist, Erin Donaghy, was doing all sorts of work in the Chumstick Basin, and she was working with these tuffs that were in between all these arcosic sands and conglomerates between Wenatchee and Leavenworth. And her advisor, Mike Eddy from Purdue, did his work on the Golden Horn. We're back like 49
Yeah.
million years ago. And I think they tied those things together. I think those are ash fall deposits 49 frickin' million years ago. I don't know if they've published on it yet, but like, there's my answer. So I guess it is possible if you know what to, like you say, if you know what to look for in a sedimentary basin.
Yeah.
God, you could match up with some of these older calderas.
It would
Wow.
be, I believe the technical term is tedious as hell,
Yeah, all
but
right.
it's certainly, I mean, and
Uh,
it would be serendipitous. You'd have to find
yeah,
something that's datable.
yeah,
But yeah,
yeah.
I'm not saying you can't do it. For
No, you're
instance,
not.
over here where I live is the Chuckanut Formation,
Mm-hmm.
Eocene sedimentary sandstones,
Right.
but just right out here on the coast in Chuck and Larrabee State Park, a there is a tuff deposit.
Yes. Yes,
It's a
it's coming back. It's coming back. This
it's
this
about
guy.
4 inches thick, and it's been folded and tilted, so now it's a vertical ash bed. But it's the age of the Chuckanut, so 40 some odd million, 50 million years old. Where did it come from?
Where'd it come from? It came out of the sky. It came from somewhere.
Yeah, but
Jeez. Okay.
we
Yeah.
don't have any volcanoes that age.
Wow. Really fun, man. Okay.
Okay.
Well, yeah. Let's finish your slideshow. You've got a few more. You're knocking this one out of the park, Dave. Keep going.
Okay. Well, I'm going to dig into something a little bit different here. I'm going to
Oh
show
boy.
a funny picture.
Oh, wow.
These are
Okay.
all my samples from Hannegan. I
Oh,
had hair
really?
then. I had
You
hair
sure?
then. These are all my samples. And I mean, this is the amount of field work and sampling it takes to tell a story, a chemical
Hmm.
story, a lithologic story.
Hmm.
And then all of these are, of course, based correlated on geologic maps. So we're to really tell the story of one of these calderas, we've got to do a lot of work.
And all those samples were from inside of the caldera.
Yes, yeah,
Okay.
it's
Yeah.
most of it's in the national park.
Ah,
And then I'm going to show another interesting one.
great.
Let's do that one. So this is just south of Hannegan Pass.
Okay.
Hannegan Pass is off to the left here. This is a photo when I did some field work in here with Jeff Tepper, our
Hmm.
mutual buddy.
Hmm.
Jeff, by the way, did his master's thesis immediately adjacent to the Hannegan
Ah,
on the Gabbro of Mount Seafric.
okay.
So when he got out of the Gabbro and got into the, at the time, undescribed volcanic rocks, he stopped because that was outside of his project.
Uh-huh.
And when I went northwest and got out of the volcanic rocks and into the gabbroic rocks, I know, okay, I'm in Tepper's old thesis area. I don't need to go any further because I'm outside the caldera.
Makes
This is
sense.
a view looking southeast
Hmm.
uh, from just outside of Hannegan Pass.
Hmm.
And this shows post caldera andesite lava flows. So there was volcanic activity in Hannegan after the caldera collapsed in multiple places that erupted discrete, chemically different lava flows.
Hmm.
These are lake filling sediments over here in this light colored stuff.
Okay.
So after the caldera collapsed, water ponded in there. I don't know how big the lake was.
Yeah.
Let's say, just for grins, let's say, a half a mile or so.
Sure.
And it filled up with silt and clay and left fossils. So there are leaf fossils in this stuff. It's clearly younger than the caldera rocks, which are these things.
Uh,
And I think older than the lava flow. So
that's not the caldera rim there on the left, is
no,
it?
no, no,
Okay.
no. The caldera rim is another. I'm mixing my distance, my scales here, but another mile and a
Sure.
half to the north, off to the left, is the caldera rim.
So was there a pattern
Uh,
to those andesitic volcanic centers that came up after the caldera collapsed?
no, they're just scattered around
Ah,
throughout the caldera.
okay.
Uh,
Thank you.
this is a view. This is Ruth Mountain,
Jesus.
south of Hannegan Pass.
Wow.
That right there, that notch,
Yeah.
is the caldera margin. That's the
Is it?
eroded caldera fault.
Love it.
So non-caldera rocks, caldera rocks.
God.
And this fault boundary runs down here, right
Oh,
down the shadowed
yeah.
area.
Kind of.
Non-caldera, these are caldera filling rocks. This big block over here on the far left on the skyline is
Yeah.
a multi is 100, maybe 200-meter wide block of phyllite from outside the caldera that fell into it.
Really?
So this is marginal breccia, caldera breccia.
On
In the Culshan caldera, Wes mapped out a slide block of Nooksack formation that
yeah.
is a kilometer in extent. It was just a big slab that slid into the caldera as the caldera is collapsing.
One block that was a kilometer across?
One block, and it is about 600 meters into the caldera.
My goodness.
So it's really cool stuff.
Yeah.
It
Yeah. This
Ideally you got some good erosion going on to give you these cross sections and exposures. Because if
right.
you're just walking across the surface, then you would find, oh, this rock ends and this rock starts, and then you're into this rock, and then you're into this little block. And if there hasn't been this erosion to give you the cross sections, you really can't tell the story very well.
Which makes this kind of a one of a kind place. I don't know. My gut feeling is like if you went to 15 of the other spots on your yellow poster, I don't know if you'd come even close to this kind of vertical cross section exposure to see some of these
Well,
relationships.
like I
Maybe.
said, I have not been in
Yeah.
there into
Yeah.
those places, so I
Right.
really, I really
Yeah.
can't say.
I just
But
imagine a
I've
bunch of
got a
trees.
lot of a lot
Yeah.
of photos. For instance, here is another lava flow in a different location within the Hannegan caldera. It's my
Huh.
friend Stephen Slaughter down here did my field work.
Oh,
Maybe you know
sure.
Stephen. He did his
Former.
masters. He did his masters at Central.
He sure did.
And then here's a dike
Mm.
that's cutting the lava flow. So the lava flow is younger than the caldera fill, and the dike is younger than the lava flow.
Mm.
So
Mm.
that's the beauty of deep erosion, is you get lots of really cool stuff to see.
Yeah.
And hopefully you get enough information to put together a really, really good story.
Well,
because
you got,
that's really what geology is, Nick, is telling good stories.
I agree with you. I
And
agree with you.
I think maybe that's why I like to do it.
Well, let's do a couple final things. I mean, boy, I'm still processing some of that really great stuff. Um, the last couple of shows I've done with these live streams, we started thinking about uplift and when the uplift in the Cascades happen and why the uplift is happening. And we're way on another big tangent here. What if
Yeah, it's pretty
do
big.
you have any thoughts about that? Like, is it all Pleistocene uplift? I mean, I know the glaciers are doing all this beautiful carving to show you what you just saw in those photos, but have you thought at all about that? The timing of the Cascades uplift?
No, I haven't really gotten into the Cascade uplift story at all, Nick. I'm more interested in the volcanic history, especially
Yeah,
these fantastic, very dynamic and very short-lived calderas.
right.
The one aspect of it's not so much uplift as the erosion that I'm interested in, because it's the erosion that gives us these exposures.
Yeah.
And I don't have a photo of it, and I really wish I had keyed one up. But in the southwest quadrant of the Hannegan caldera, the surface rock is are plutons, small plutons that intruded the caldera. So these are rocks that are younger than the caldera, but that crystallized about 2 kilometers deep and are now the surface. So that tells us that there's been about 2 kilometers of surface stripping since the caldera eruption in order to expose these post caldera plutons. How's that for a
Didn't
mind blower?
Well, it is a mind blower, and I would be totally off balance, except just recently I think I was showing Paul Hammond's work where he's like, yeah, we've got Mount Aix caldera, and then here comes this Pluton that's younger that's coming
Yes,
up through this thing.
absolutely.
Is that a thing? Is that a
Oh, yeah.
pattern? Well,
Oh,
I
yes.
mean,
I mean, you got to have enough. I mean, the magma is still there, right? It doesn't go away. And so the magma body crystallizes over time. And if you erode deep enough, then you expose the magma body, or the magma intruded further upward into the caldera fill. And then with luck, it's exposed. In the case of Hannegan, the highest elevations in the caldera at Icy Peak and Ruth Mountain expose these caldera post caldera intrusions.
hmm,
In the case of the Culshan caldera, there is a very small body of granodiorite, essentially, that is less than 1 million years old. A small stock that intruded the caldera fill. It's been badly leached and altered, so we can't get really good dating on it, but
hmm.
it's clearly younger than 1 million years old. So this is a body that cooled within the crust and is now exposed. So it's erosion that lets us see these things,
Yeah.
and it occurs at a phenomenal rate in the Cascades.
What's happening at a phenomenal rate? The crystallization of the
Erosion,
Pluton erosion.
erosion. So in
Yeah.
3 million years, we have stripped at least 2 kilometers of surface rock
Right.
away.
Right. Well, that's how we'll finish this whole winter. I've been so surprised, and I think many of the viewers have been surprised how topographically low the Cascades are until recently in the last 10 million, last 7 million, last 3 million years. And we're trying to come up with different ways to keep track of those paleo elevations,
Yeah, yeah,
essentially.
yeah.
So, we're at sea level. The Ohanapakash is doing all sorts of crazy stuff, and we're underwater. We're above. Maybe you can do some of. Can you do some of that with these plutons? You do geobarometry to figure out.
Precisely. You can do a geobarometry. You can go into apatite barometry. We're not going to get into that on this talk, but
No, no.
that's what tells us at what depth these bodies cooled,
Hmm.
and they're at the surface now, so they're essentially at zero depth.
Right.
Yeah, and they form mountain peaks, 7,000-foot high mountain peaks in the Cascades today.
Wow. This is amazing. All right. I'm going to have to go home, have a good roast beef sandwich, and think about this for the next 3 hours. You've given me a lot to think about.
Oh, good. I don't want you to be bored, Nick.
No, no, I am definitely not bored, Dave. Any final comments before we sign off? I'm going to stop the recording here, but anything else you wanted to add? You've just felt like what have we done today?
There is one thing I want to say.
Yeah.
It was on your Hammondland talk the other day that I learned that Paul had died.
Hmm.
I was sorry to hear that. We only collaborated on that one paper, one Caldera paper, but it seemed like there was more to come.
Yeah.
But he's just kind of having a hard time pulling the trigger, even 2009, of getting things published. And we disagreed on some things, but we got along really well and really wanted to do field work together and didn't get to do much. I was really sorry to hear that the old codger had finally kicked the bucket. Hell of a guy, though.
He was a hell of a guy, and you're a hell of a guy. Thank you for your time today, Dave. Yeah, let me stop the recording. We'll talk for a couple more minutes. Thank you so much.
Sure.
Great job today.
Great. Good to be here.
All right.
Thanks.
Thank you. Bye-bye.